we're on our way to the end of this long list of different functions that we can differentiate. So in this video, we're going to start looking at more derivatives of exponential functions and then also some derivatives of logarithmic functions. So we already have the derivative of the natural exponential, I guess we can call it, y equals e to the x. And what we want to do now is to get the derivative of the natural logarithm, its inverse, and then also the generalized version of each of these, just any old exponential function like 4 raised to the x power and any old logarithm function like log base 2 of x or something like that. We're also going to come up with a nice way of generalizing this differentiation of inverse functions, and we'll be able to use that later on in the course too. So here we go. Let's just first give a quick recap of inverses. There's lots to say here, but I'm only going to say a couple of things that'll be important for now. One of the basic ideas of an inverse is that if you have some function f of x and we say that that's equal to y, then for the inverse we can say x is equal to the f inverse of y. We switch the inputs and outputs. That's really the basic idea of what an inverse function is. It goes backwards through your function. So it takes what was an output of your function and spits out the corresponding input. Now we also have a nice composition property that says if you have a function composed with its inverse, or f of f inverse of x, that's just equal to whatever the input, in this case x, was. And the order doesn't really matter here, right? An inverse composed with the function f, or f inverse of f of x, is just equal to x as well. So we'll use this property and see how things go. All right, so we want to find the derivative of the natural log. We're going to use this property where we change the inputs and outputs. The natural log is the inverse of the natural exponential e. So if we let y equal the natural log of x, then this is going to lead us to x equals the exponential e to the y. And then now we can use implicit differentiation on this equation here. Because this equation represents the same relationship between x and y as this first function natural log of x does, then what we can do is just say if x equals e to the y, then d over dx of x is equal to d over dx of, oops, not e to the x, e to the y. There we go. And now, again, just use implicit differentiation. The derivative of x with regard to x is 1. And now we've got to use some chain rule over here, right? So this is y prime e to the y. And now it's pretty easy to solve for y prime. We can just divide by e to the y. But remember, we said y was natural log of x, so let's just go ahead and put that in here. And here we go. We have y prime is 1 over e to the natural log x. This is a function composed with its inverse. It's just going to spit out that output 1 over x. Okay, so that was kind of weird, right? We used the inverse representation of that function, right, where we switched the variables around, and then we used implicit differentiation to find that derivative. This is a pretty slick trick that we've got. So here's our quick little derivative of the natural log summary. For the natural log of x, the derivative is 1 over x. And we'll say, okay, that's only when x is greater than 0 because that's the domain of the natural log function. You might remember what the graph of the natural log looks like. It looks like this. It's the domain of the natural log function because that's the range of its inverse, the exponential function. So that's what we've got. We can change things by throwing some absolute values around the input, and now it can take in positive and negative values. And so then we have that the derivative is 1 over x as long as x isn't 0. Cool. All right, the general logarithm now. We need to remind ourselves of this change of base property of logs. I'm going to go over a couple of different properties of logs. And if you don't remember all those things, it's no big deal, but just look up these names. This is the change of base property. It means that you can rewrite any logarithm in terms of any other logarithm. So technically, the change of base property says this, that log base b of x is equal to log base a of x over log base a of b, where we can pick this new base a to be whatever we want. Normally, we either pick 10 or e. We use either a common log or a natural log because those are the two types of logs that we typically have on like a calculator or something like that. But anyways, we're going to rewrite this log base b in terms of the natural log. And now, hopefully, it's easy enough to see how to differentiate log base b of x. This is just the derivative of the natural log of x over the natural log of b. B is just a number, and so that means the natural log of b is just a number. It's a part of the coefficient. And so what that means is that I can factor it out. So now we're looking at 1 over natural log of b times the derivative of the natural log of x. We just found this thing. So this is really 1 over the natural log of b times 1 over x. We commonly will write this way. 1 over x natural log b. We'll combine those fractions together, get that nice denominator. And this is what we're looking at. Here's the little summary. So for b some base that's positive but not 1, the derivative of log base b is 1 over x natural log of b. And again, we still have that same domain where x is greater than 0. And we can do the same trick where if we use absolute values around the inputs, that means that we can take in negative x values. And so we just have a domain of x not equal to 0 there. So those are our logarithms. Now what we'd like to do is to come up with the general exponential derivative, the derivative of b to the x. Well, notice once we have this derivative of the log base b function, we have the derivative of its inverse, so we can use that same trick. Right? We can say if y equals b to the x, that's really the same thing as x equals log base b of y, and we can use implicit differentiation to find the derivative of y. So same trick that we use to start things off to find the derivative of the natural log. We'll just differentiate both sides of this equation with regard to x. And notice again we have some chain rule, so we're going to have a y prime times 1 over y natural log b. Again, this is the derivative of this logarithm with regard to y times the derivative of y with regard to x. And now you can see that y prime is equal to y natural log b, but y was b to the x, so y prime is b to the x natural log b. And that is your derivative rule for the general exponential. Notice that for the exponential e to the x, our derivative was e to the x without this natural log component, but that's because the natural log of e is just 1. So really that coefficient that we were multiplying there was just 1. Awesome. So there's our derivative of the general exponential for the function b to the x, where again that base is some positive number that's not 1. The derivative is b to the x times the natural log of b. There's another way that you can prove this, and it's just by using the chain rule on this composed function. What we're doing is we're composing a function and its inverse, right? If we wrap a natural log around this and then throw it into the exponent on e, those things undo each other. But there's another nice property of logs that says for the natural log of b to the x, we can take this exponent and write it out front as a coefficient. So if we're looking at y equals e to the natural log b to the x, that's the same thing as y equals e to the x natural log b. And now we can find the derivative by just using the chain rule, right? This part here is our u that's composed on the inside of this thing. Du over dx when we need it is just going to be natural log b. And so now what we can say is that dy over dx is going to be d over du of e to the u times du over dx. Again, the derivative of this exponential we know is just going to be e to the u, but u is x natural log b, so we have e to the x natural log b times natural log b. And again, we can start undoing things. Notice that this is the same thing as e to the natural log b to the x. And so this is really b to the x. So we have, again, that this derivative is b to the x times natural log b. So that's another way of doing it if you'd like. Here's a couple of examples of just using these new exponential and log rules in conjunction with some of the other derivative rules that we have. So here's some stuff that we got to think through. Pause your video. Give these examples a shot. See if you can work through these. Find any sort of product quotient or chain rule or anything like that that you're using. And then when you come back, we can try these out together. All right, the main thing to notice in this first one is that this is an exponential, but this is a power function. So we can't mix those things up. We need to make sure we understand how those derivative rules work. So the derivative of that exponential is going to be pi to the x times the natural log of the base pi. The derivative of this power function, we're going to bring our exponent out front and subtract 1. So this is pi x to the pi minus 1. And then this logarithm, we've got 1 over x, and then we also divide by the natural log of the base of that logarithm. That's by the change of base rule. So that's what we have for the derivative there. It's kind of ugly, but whatever. You could do a whole bunch of stuff to like try and clean up the look of it, but I don't know. I think it probably just looks like this. For this next one, what you'll notice is that we're going to have to do some product rule, right? I'm going to peel this part off and say this is really just a badly written version of 2x squared natural log x minus 5 raised to the 3x cubed minus 4. So for this first one, I'm going to do some product rule here. I'll say u is equal to 2x squared, and v is equal to the natural log of x. U prime then is 4x, and v prime is 1 over x. So we're going to go ahead and do this. So our derivative here looks like 2x squared over x, that's my 2x squared times 1 over x, plus 4x natural log x. And now I'm going to have some chain rule. I'll say u is equal to 3x to the third minus 4. So I have to look at the derivative of this exponential 5 to the u with regard to u. So that's going to be minus 5 to the u natural log 5. That's the derivative of that exponential times du over dx. Du over dx we can see is going to be 9x squared. So let's write all this stuff together. This is 2x plus 4x natural log x minus 5 to the 3x cubed minus 4 natural log 5 times 9x squared. And you can bring that 9x squared out front. It doesn't really matter, but there's not really much more to do with this other than leave it like that. You could, again, do some rewriting of things and see if you can kind of find some common factors and whatever. There's nothing nice that I can see right off the bat, though, other than a factor of x. You could pull a factor of x out of this whole thing, and that's it. Last example, this one's a really fun one. Just take a moment to look at this and try and see why this is going to be really frustrating to do. Pause this video and hopefully come back. Don't leave out of anxiety because this does look like a pretty terrible derivative to find. Do you see what the issues are? Oh, good God, do we have so much going on here, right? So look at this. We have all of this inside of a log. So there's some chain rule going on. But then notice that we really have products of 3 different things, but some of those things have composition in them. Oh my goodness, look at all the layers, look at all the things that we're going to have to do. Whew. Wait a second, let's remember something about logarithms that's really nice. Logarithms have these great properties, and we'll talk a little bit more about these properties in our next video. Logarithms have these great properties where products of things inside of a log get split to become sums. So what we can do is rewrite this as the natural log of x squared plus the natural log of x plus 4 to the 14 plus the natural log of x minus 10 to the 19. Well, that's pretty nice. We split this annoying three-way product rule into just a sum of things. We also have this great property where these exponents, not through differentiation, but through properties of logs, come out front as coefficients. And again, if you don't remember any of these properties of logs, just go ahead and look some of these up. They're no big deal. So we haven't actually differentiated anything yet. We're still looking to differentiate this, but now we've turned this function into 2 natural log x plus 14 natural log x plus 4, plus 19 natural log x minus 10. This is a way easier function to differentiate. Sums are easy to work with. We'll just apply this derivative to each thing. And then you're also going to notice that, yes, we have some composition, right? There's this x minus 4, and there's x plus 4. I keep wanting to say minus. And then there's an x minus 10 inside. Oh, and I forgot my derivative here. There we go. There's some composition inside of these logs. But notice the derivative of each of these inside pieces is just 1. So if we were to set this equal to u and maybe this x minus 10 equal to v and do the chain rule on these, we're really just going to have like the natural log of x plus 4. That derivative is going to be 1 over x plus 4. We've got some coefficients, but this should be pretty easy to differentiate. Done. And that's again because the natural log of u's derivative with regard to u is 1 over u. So that means with regard to x, the derivative of the natural log of u is equal to 1 over u times u prime. Or sometimes people will write it as u prime over u. But in this case, the derivative of each of these inside pieces is just 1. So again, there's really like a little 1 being multiplied here, but we don't have to write that. So anyways, that's a really fun example because it looks terrible at the very beginning, but it's really not so bad. So that's exponentials and logarithms. Hopefully, we'll use enough of these in examples that we'll get used to these derivative rules pretty quickly, and we can move on and start collecting more and more. Before we jump into our last set of functions to learn about the derivatives of, the inverse trig functions, what we're going to do is take a little sidebar and talk about logarithmic differentiation. That's going to use these properties of logs that we've looked at in this last example to see if we can take a look at some weird function types and differentiate them using a pretty clever trick. So that's what we're up to next.